Now we start moving into the serious stuff. In Chapter 5, we're going to look at series circuits. We're going to start applying what we've learned about Ohm's law and Watt's law, power, to help us solve for an analysis, to do analyses on actual circuits with actual components. So where we're going to start off very simply is the series resistor configuration. So we're going to look at total series current in a circuit, at the application of Ohm's law, and then we'll look at voltage sources in series, learn about Kirchhoff's voltage law, voltage dividers, power in a circuit, voltage measurement, and then just touch on troubleshooting, which you get in your lab. So there are your objectives, pretty much just what we just discussed in the previous slide. And the terms that you're going to have to get used to using. What is a series circuit? How does that differentiate from a parallel? What's the difference between Kirchhoff's voltage law and that of Ohm's law? Looking at voltage dividers to help us solve for circuit configurations. What is a ground? What's an open? And what's a short? So in identifying a series circuit, primarily, any circuit where we string together end to end a group of components, in this case whether it's 2 resistors, 3 resistors, or 4 resistors, if they're connected in this configuration, we call them a series circuit. So we're going to find out mathematically how do we compute the total resistance in a circuit, and then how can we from a total resistance determine an unknown resistance value. So when we look at a resistor, the way they're laid out on the circuit board may not exactly match the way the schematic is drawn out. So we can see that in this series circuit configuration, we've got lots of configurations that we can look at, and every one of them is a series. As long as the end of one ties to the end of the other, whether it's 2, 3, 4, 6, 8, it doesn't matter. If they are tied end to end, they become a series circuit, and what we'll see is that the current that passes through this configuration is the same current that goes through every one of the resistors. So if you know the current in one, you know the current in all of them. Now the difference will come when we start looking at voltage, because the resistance and the current will help us calculate how much voltage is dropped across each of these resistor components. So if we look at what a typical breadboard configuration would look like, in the first example it says, suppose there are 5 resistors positioned on a protoboard as shown. Wire them together in series so that starting from the positive terminal R1, first R2, R3, and so on, and then draw the schematic diagram. So as we go through here, now we need to learn about what's going on a protoboard. On a protoboard, any of these vertical points on here are connected together. So when you plug a wire, a jumper wire, in this hole and plug it into this hole, it becomes a series path. So you notice here that as we're going along, we create each of the paths here by plugging into the correct hole into the protoboard. And so out the other end, our total resistance actually is across A and B when we connect all 5 of these resistors together. Now if we try to draw them similar to the physical configuration, you can see in this simple schematic that we have here, we've got 1, 2, 3, 4, and 5 all connected pretty much the same way you see them on the protoboard. That may not always be the case, so you've got to get used to looking at a schematic diagram and determining what it really looks like physically, and looking at the physical configuration and being able to sketch what it looks like in the schematic diagram. So we can see here on this board here, which is actually a printed circuit board, you can see how each of the resistors, although they're laid out in this configuration, when you connect the runs together on the board, you can see that it does, in fact, on the top here, form a series circuit from pin 1 to 2 and a series circuit from pin 3 to 4 on the bottom here. Okay, so in this exercise they say if we assign values accordingly, 2.2 k ohms, 3.3 k ohms, 1 k ohm, etc., etc., we can sum these together in each of these tracks, pin 1 to 2, pin 3 to 4, and calculate what the total resistance is for the circuit board. So in this case, if we sum resistor 1 to resistor 7, we would end up with a summation, the full arithmetic summation for that total. The same thing applies with the second one. So we've seen here why resistance values add when resistors are connected in series, and we can start to look at how do we apply the mathematical relationships. So series resistors values add in the arithmetic summation. So if we look at A, B, and C here, we can see in each case we've added a 10 ohm resistor. In B we add and then we added another 10 ohm resistor in C. So in this circuit A, we only have one 10 ohm resistor. In this circuit B, adding a second one, we now have a total of 20 ohms because the circuit only sees the total resistances, and 3 we have 30. And so you can see why if you take measurements within a circuit, you always have to remove the resistor under test. It has to actually physically be removed from the circuit. Otherwise, the meter will try to measure all of the resistance in the circuit. So mathematically, series resistance formula is really just the sum. So R sub T, or R total, then equals resistors 1 through the very last resistor, and that's what that R sub N. So if you see a little N here, that's telling you out to the nth resistor in the circuit. If it happens to be 4 resistors, then we have R1, R2, R3, and R4, gives us our total. If there are 6 resistors, 1, 2, 3, 4, 5, 6, added together gives us our total. So if, from the previous example here, we had a 56 ohm, 100 ohm, 27 ohm, 10 ohm, 47 ohm, when we add these together arithmetically, we get 240 ohms of resistance total. So you could, in essence, you could take all 6 of those, all 5 in this case, all 5 of those resistors and replace it with one resistor and call it R total, and it would be 240 ohms of resistance. So again, if we look at it on a proto board, you can see here we've divided it up across this bridge or this well, and we've got everything connected on this side and everything connected on this side between R1 and R5. So in this case, with the given values, if you went through and calculated these with the color codes, you would find that you had a 33 ohm, 68 ohm, 100 ohm, 47, and 10 ohm resistor. Okay, if I wanted to turn them into a series connection, you can see that if I jumper from R1 to R2, R2 to R3, R3 to R4, R4 to R5, and then to point B, it exactly matches the schematic diagram. So you're going to get lots of practice in your lab actually building these simple circuits and building on these circuits to build more complex circuits as you start moving through your curriculum. So in this example, what is the total resistance in the circuit shown? So we've got a 39 ohm, 100 ohm, 47 ohm, 100 ohm, 180, and 68 ohms. So all we have to do is sum all of those values, and we get a total of 534 ohms for the resistance. As I said before, you could take all of these, combine them into one resistor, call it R total, and that would be the value. The related problem asks you to change the values and calculate the total. I'll let you do that. So in this circuit, they're giving you an idea here of using a piece of equipment here. Okay, so they want us to determine the value of R4, which is the one in red down here, in the circuit. So in this case, from the ohm meter reading, the ohm meter is telling you that the total resistance is 17.9 k ohms. So if you add all of these resistors plus the unknown together, which you don't know, you would measure 17.9 k ohms. Well, how can I determine what R4 is? Well, in this case, if I take 17.9 k ohms and I subtract 1k, 2.2k, 4.7k, whatever is left over, in this case 10 k ohms, ends up being the value of R4. So in problems like this, if we were given a total resistance, whether it was a meter reading or it was just given, and you knew 3 of these, you can solve for the 4th very easily. Again, the related problem I want you to solve. Equal value series resistors. Okay, so what if I had a set of resistors and they all had the same value? Well, let's just read what this says. When a circuit has more than one resistor of the same value in series, there is a shortcut method to obtain the total resistance. Simply multiply the resistance value by the number of equal value resistors that are in the series. This method is essentially the same as adding the values together. So for example, 5 100 ohm resistors in series has a total resistance of 5 times 100, which gives us 500. Okay, so 5 times 100 gives us 500. In general, the formula then is expressed as total resistance is equal to the number of resistance times the value of the resistors if they have the same value. So in our example here, let's say we want to find the total resistance of 8 22 ohm resistors. So we could add 22 and 22 and 22 and 22 and 22 and 22, and you can run that through your calculator, and you would get 176 ohms. But it's much easier to say, well, let's take 22, multiply it times 8, and I get that same 176 ohms. So resistors in series with equal value very simply becomes a quick product of the number of resistors times the value. So before we move into current in a series resistance, let's go ahead and stop here and think about what we just put together, and we will move then into current.